Okay, so second order of derivatives. We know we can. We can keep differentiating until the end of time, until we run out of things to differentiate. That's the thing. And in some particular instances, can you tell me one thing that we can completely continue to differentiate forever? What was it? Yes. Sine and cosine. Trig, you definitely can. E to the x. Remember we talked about e to the x becomes e to the x. So when you differentiate it, what it becomes is e to the x. And when you differentiate it, it becomes etc., etc., etc. We can continue to differentiate it forever if it's just straight e to the x. And we will be still got e to the x at the end. But we're only interested in differentiating twice. And that's because there is information to be had from differentiating twice. Okay? So how do we write differentiating twice? We've got two methods, y double dash or d squared y over dx squared. We'll talk about that one a little bit later on, so just hang with it at the moment. So if we've got y equals 5x cubed plus 3x minus 2, then y dash will be 15x squared plus 3, and y double dash will be 30x. No problems there. So the first derivative tells us what? It's the gradient function, so it tells us the gradient. All right? Tells us whether a graph or a function is increasing, decreasing, or has a critical point, which we can call also a turning point. All right? Our second derivative gives us a whole lot more information around a graph. So, not specifically for a graph though. All right, so it can be for a function as well as a graph. But anyway, so if we've differentiated, let's say we've got y double dash, I'm going to go to f double dash of x because I want to substitute for x. So if I substitute for x and I get a negative, all right, this is giving me a certain amount of information. It could be that if x is a turning point, it will tell me whether or not my turning point is a maximum, a minimum, or perhaps something else. There's not a lot of other choices, probably a turning point, but it tells us that something is happening at that point. All right, so we've got, if f double dashed of x is less than 0, anybody know? Yeah, so the temptation is to say because it's less than 0, it's going to be the minimum point, but it's actually the opposite, all right? So it implies that x is a maximum point. And if it is greater than 0, then that implies that x is a minimum. But if x, or f double dash of x is equal to 0, there's a number of choices. It could be a stationary point, a point of inflection. It will be a stationary point. Could be a stationary point, but it doesn't actually necessarily have to be a stationary point. It's only when we've already tested to find out that f dashed of x is equal to 0 that we can then go to the f double dash of that same x. If it's equal to 0, it could be a stationary point. So that's a point in time where the gradient becomes 0. Unfortunately, though, it's not a rule that it is a stationary point. So We've got two choices here. We can think about the graph and what the graph looks like and make a decision based on that. Or we can test points very close, so the A minus A plus points, very close to this X that gave us 0. So in fact, if we have this scenario, so it's gone like this, or there are situations where f double dash can be a maximum or a minimum, by differentiating it again, we could find out a little bit more about this particular scenario, the triple. So, we've got a graph. Let's just have, let's have a look at it. So we've got a graph of this. What is it? A quartic, right? X to the power of 4. This is f of x. When we differentiate it and we get f dash to the x, we've got, we need an axis. Put an axis in. Doesn't matter where the axis is in the top one. Let's put it here. All right. We've got a 0 gradient, a 0 gradient, and 0 gradient. All right. So we've got increasing, so above the line, increasing means positive, round, like this one I missed, but that's okay. We'll smooth it off, make it bigger. All right, so that's what the gradient function looks like. The gradient is positive, so it's above, it's 0, it's negative, so it's below, it's 0, it's positive, so it's above, 0, negative. Right? Understand? Shouldn't be new. So what does f double dash tell us then? So f double dash is the gradient of the gradient function. Correct? So what is happening here? We've got, yay, it's not us. Every time I hear it, I think, thank goodness, it's not us. Right? So we've got a negative gradient to here, negative gradient, positive gradient, negative gradient. Yes? All right? So at this point here, it's about here somewhere, this point. So our second derivative is negative, it's a positive. Right? Our second derivative of this point here is positive, therefore it's a minimum point. Maximum, minimum, maximum. All right? So what does f triple dash tell us? I'm going to calculate, but read. Tell us. It's the gradient of this. This is positive. Here somewhere there's a dot. Where does that point line upwards? That's 0. That's approximately there. And this is approximately here. And we've got positive gradient. Right. So we've ended up with this. Going through 4 derivatives. This one has told us when points are increasing and decreasing. So decreasing, increasing, above the line, decreasing, increasing, decreasing, points, minimum points. This one is telling us this story. So this one here, this point here, all right down here, is actually this one here, if I lined it up. So negative, negative, positive. All right, so we've got a maximum point, a minimum point, a maximum point. We've also got something here and here. This tells a story too. All right, it actually says that there is a change in the concavity of this graph at this point. So being a minimum here, this graph is going between concave down and concave up at this point. So this is telling us that these 2 points are actually points of inflection, because a point of inflection is between concavities. It's just that these two are not turning points because they don't have a gradient of 0. All right? So they're still points of inflection. Points of inflection do not only have to be turning points. They're between the points of concavity. So up here we've got concavity down, still down, so that's all this bit here, up, here, down. So this is telling us more about the graph. This is this part here. So concavity is being told by the F double dash as well. Oops, concavity. So if the concavity, F double dash, is less than 0, we have concave down. If F double dash is greater than 0, we have concave up. If we have the concavity equal to 0, F double dash, we have another point of inflection. But not necessarily a turning point. Casper.
Your read graph is wrong.
My read graph's wrong. Now it's right, hey?
Yeah.
Okay. We haven't got to talk about that one yet. That's good. So all we're left with this is this, and this piece of information only tells us that this point here doesn't give us any more information than that this point here that this point here is a point of inflection on this graph, which means on this graph this is our minimum. So it's actually not very helpful at all as far as graphing is concerned. And we never actually asked to use it except for here. So